You have a 1,000,000-watt smile. That is a saying that conveys happiness, an emotion that humans are generally good at recognizing. Can the same be said for a machine? So I'll start off this talk slash tutorial and just explain a bit about facial expression recognition. And then I'll discuss the major aspects that you have to consider when implementing a convolutional neural net. So I'll talk about pre-processing, augmentation, transfer learning, network architectures, and how to report on your results. If you're feeling a bit tired, then just pay attention to the green slides. That's where I give away hints and recommendations. Okay, so humans convey their emotions across in various forms, one of which is expressed through changes in a person's face based on their emotional state. So facial expression recognition is the ability to recognize these expressions being conveyed through these changes. In the 18th century, Darwin discussed the universality of emotions across mammals. In 1971, Augment proposed 6 emotional classes, namely happiness, sadness, anger, surprise, disgust, and fear. An automatic facial expression system is one that can automatically recognize expressions. Given an input image, it has to tag the images accordingly. In 1978, there was the first proposed automatic facial expression system. Here's an example of Microsoft Emotion API, and this is what is expected out of an automatic facial expression system. So here, it correctly got the emotion with a probability of 0.99 on anger. So I'll discuss a few applications. Pain is usually self-reported verbally. In this study, quote, if the patient is a child or has limited ability to communicate, mentally impaired, or patients have assisted breathing, self-report may not be a viable measure of pain. So here, an automatic facial expression system could be vital. In this study, the authors state, quote, a social robot would be able to encourage a cancer patient to take their medication in a more efficient manner if it were able to understand the emotional state of the patient. This is another interesting study where there's a teacher and there are students in a remote environment, and there's a webcam which is monitoring their emotional state, which is providing feedback back to the educator. Some other applications of expression recognition include monitoring stress. It could be stress while driving, stress while in a flight, an alternative to the capture verification system that requires you to click on something or to solve some puzzle, assisting with people with autism and human-computer interaction. Okay, so over the past few months, I've surveyed 100+ articles on this topic. So essentially, I've done the dirty work for you, and I'll be providing these insights that I've gathered. So I'll be discussing each aspect in a step. So I will go step 1, step 2, step 3, and so on. And so these are studies specifically related to image facial expression recognition using CNNs. Okay, so the first step is to get a data set. And these are the data sets that have been reported in the literature. So there's a number that you can choose from. I'll just leave this on in case anyone wants to take notes. Most require that you obtain permission from the author. In addition, they have restricted licenses, so they're for non-commercial purposes, which becomes tricky for authors that are working in companies. The earliest data set was released in 1994, and the most recent in 2017. So here I present the top 5 most used data sets in the literature, and I've ordered them according to the usage, which is on the first row. And amongst all the possible characteristics, I've selected 3 characteristics which I consider to be interesting and useful. The row that says posed and lab refer to data sets that have images of people that are posing their expressions in a controlled environment. So when it says yes, that means that is the case, and no means it's not the case. The other interesting characteristic is the gender balance. Here it is a male to female percentage and age. So there are limitations with some of these data sets. Both of these images express sadness. The image on the right, on the other hand, is from a posed data set. And the image on the left is just an image that I got off the internet. So I could be wrong, but if I'm sad, I don't look like the person on the right. And I think it would actually hurt to just have that face on the whole time. So the image on the right clearly is very unrealistic. So that is a limitation of using a posed data set. Other limitations include the effect of lighting. So in these posed data sets, there'll be a photographer and there'll be multiple lighting sources, and the lighting sources will remain constant, so it's generally good lighting sources. This is not the case in realistic images. The other limitation are the unrealistic poses that people use in these data sets. And actually, in one of the data sets, they used amateur actors, and they asked them to rehearse ahead of time. So incredibly unrealistic. So all of these aspects do not reflect realistic images in an uncontrolled environment. So let's take a step back. What actually makes facial expression recognition challenging? Well, variations in light, if you have a beard or mustache, so facial hair, ethnic diversity, difference in age, if you're wearing sunglasses or glasses, and your head pose. So these are all aspects that make facial expression very challenging. So here's a question. Do you think that if I train a CNN on images of young people smiling, do you think that there is a problem here? So we're training images on just on young people smiling. So here is an image of someone relatively young, and here is the filter that was learned. So this is not a CNN. This is a different machine learning method. And those are the filters. So here is someone slightly older, and this person is not smiling, but the same fold on their face is present. And that is definitely an issue. So let's take a step back at these data sets and ask ourselves if these data sets that are reported in the top 5% of the studies are actually sufficiently good. Well, 3 of these data sets consist of posed images. So that's definitely a problem. Yet, a large number of studies in 2017 are using these posed data sets. So this raises some questions. In terms of the literature, a lot of authors, as I mentioned, a lot of authors are using these posed data sets. On average, authors reported on 2 data sets. Why is this the case? Think about the no free lunch theorem. Is it sufficiently okay and representative to report your results on just 2 data sets? Some of the authors describe the way in which they create these data sets, 2 of which, so one of the 2 used 6 keywords, and the other used up to 1,000 in 6 different languages. And they use Google, Baidu, and Bing to collect the images. The other issue is, in the studies reported in literature, is that authors sometimes collect their own data set and don't release this data set. By not releasing it, comparisons become difficult, and then they'll say something like, we've achieved state of the art, but how can you compare? So it's not fair. So my personal recommendation is that I would definitely use the CK Plus dataset, the Japanese facial expression dataset, and the FIR 2013 dataset, despite some of the limitations. And the rationale is that I would use this for benchmarking against all the existing studies. However, I do encourage using datasets of non-pose expressions, as this is a trend in the literature moving forward, and also represents more realistic facial expressions. I recommend working with 3D data, which is images obtained at different angles. This is also a trend in the literature. And humans don't actually express their emotions just in 6 out of the 6 basic classes. There's a study that describes the combination as compound expression. So it's a combination of these 6 expressions, such as happily surprised or angry, disgusted. Okay, so step 2. So we've got our data set. Now we need to pre-process our data set. So we essentially want to transform the images to increase the accuracy of the CNN. So consider a data set that has very irregular lighting conditions, such as the images on the left. It would definitely be more suitable to convert the images in some way to get the image on the right. So here our objective is to try and assist the CNN by performing some transformations. So one of these transformations include resizing. If you're using an existing architecture, then you definitely want to resize your input image to meet the requirements of the architecture. In addition to that, I found that some authors just generally use resizing for many other reasons. If you're interested in the values, what they used is they ranged between 48 by 48 to 64 by 64, and some authors resized up to a larger resolution of 256. There was definitely not a lot of consistency between the values reported in the literature, so it's very hard to draw conclusions. Another thing you can do is face detection. Here you would use it to either crop faces, detect faces, align faces by detecting the eyes and then checking the angle between them and then rotating the image, and also to extract useful features from the face. Cropping is also definitely used. Here you would first detect landmarks, and then you would crop the face and remove the noise and extra irrelevant regions. For example, you don't really need to know about a person's head to determine their expression. Viola-Jones algorithm is oftenly used, and if you're interested in the implementation, OpenCV was used most commonly, dlib for those that are using C++, and there are alternatives. The next thing you definitely want to do is image enhancement. And this isn't really the case in posed datasets because the cameras and the lights are set up so nicely. But if you're using images off the internet or more challenging datasets, then you definitely want to enhance your image. As you can see in the pictures, histogram equalization was used very commonly. An alternative is an ensemble of different methods: illumination normalization and contrast enhancement. And once again, in terms of software, MATLAB was used a lot, and In-Face Toolbox was used quite often. In terms of the literature, a lot of studies did not actually use any pre-processing. So the question is, did they omit this, or did they just not mention it? Various studies have demonstrated that if you apply pre-processing, you will have an improvement in your CNN performance. There was a study that compared 6 different pre-processing studies to not applying pre-processing, and in each case, the pre-processing was better to no pre-processing. So having said that, I definitely encourage people to use pre-processing. If you're interested in aligning and landmark detection and face detection, I would use the Viola-Jones face detection, but I would use another one in addition to that, just in case the Viola-Jones doesn't work, and also to help eliminate false positives. I would definitely use histogram equalization. That has been shown to work very well. You don't actually have to work in the RGB space. You can convert your images into grayscale. There was a study, however, and this is very interesting, and for those that are interested in research, I would definitely recommend reading this paper. They essentially transformed the RGB space into a totally different 3-dimensional space, and by achieving this transformation, they were able to improve the accuracy. So my question is, are there alternatives that can be achieved, or at least alternative color channels? Viola-Jones was reported to be computationally efficient and achieves good accuracy. It would be very interesting to benchmark all of these landmark algorithms on multiple facial expression datasets. And multiple studies have reported that decreasing the resolution of your image does not significantly reduce performance. So that's also something to keep in mind. Okay, once we've pre-processed our data, we want to augment our dataset. So the CK Plus dataset has less than 600 images, and the Japanese facial expression has only 213. And we know that CNNs work well with a lot of images, so we definitely want to augment. Horizontal flipping was used very frequently, followed by rotation, cropping in 12 studies, and zooming was reported in 6 studies. Horizontal flipping is the easiest to implement. It's one line in OpenCV. We're just swapping what's on the left to what's on the right, and essentially we can augment our data by 2-folds. Rotation requires a little bit more effort because we have to decide on the angle. Typically, this is done in both the clockwise and anti-clockwise direction. However, we have to ask ourselves, what angle are we going to use? So a lot of studies in literature did not report on this, so it becomes complicated. So 2 studies, for example, reported on 45 degrees, 1 used 30 degrees, and 2 used 10 degrees. and there was one that used an outrageous value of 90 degrees. The benefit here is we can augment our data by 4 folds. Cropping was used a lot, so I would definitely recommend that as well. Here, authors would crop on the 4 corners of the image and the center of the image. Other authors tried randomly cropping and then averaging the prediction across multiple CNNs. Once again, there was not a lot of consistency in the literature to draw any conclusive remarks. Zooming was used less often. Some studies zoomed by 10%, by a factor of 1.2. Some just randomly zoomed onto the 4 corners. Some just randomly zoomed anywhere. So there's very little detail to draw any conclusions here. In terms of the literature, 2 studies augmented by collecting additional data. Now, this is very tedious and painful. In the one, they collected 1,000 extra images per class, and the other one, they collected 2,000 images per class. Typically here, Baidu and Google and Bing were used. OpenCV was reported in 5 studies. A lot of studies didn't report what software they used. 2 studies reported the benefit of using data augmentation as opposed to using it in the context of CNNs and expression recognition. And 47% of the studies mentioned that they used data augmentation. So why is this value so small given that we know that we need to augment our data? I would definitely recommend at very least applying horizontal flipping and augment your data by 2. If you're interested in rotation, I would start with 10 and 45 degrees in both clockwise and anti-clockwise direction. Augment your data by 4 folds. Cropping is a good idea. You can crop on the 4 corners in the center, which augments your data by 5. And then if you flip each of those images, you essentially augment your data by 10 folds. So for researchers, I would investigate optimal parameters of all of these methods, because no one has attempted to do this, across multiple expression recognition data sets in a fair setting, of course. So we know that deep learning requires a lot of data, so we definitely need to augment. And a combination of these augmentations is a good idea. So for the next step, we have options. We can either train the CNN from scratch, we can use transfer learning to avoid training from scratch, or we can train an ensemble. So for today, I'm just going to talk about transfer learning. So in case you don't know, so if you train a CNN on a particular data set and then you apply it to a different problem domain, we say that we've transferred the knowledge that we've gained. So a very brief definition of transfer learning. Sometimes it can take hours or days to train CNNs on large data sets, especially if you have a very big architecture and if you have limited hardware. So why not take advantage of transfer learning? If you do make this decision, the first thing you want to do is make copies of your grayscale image. Because sometimes your architecture requires multiple channels. So if it needs 3 input channels and you have 1 grayscale image, you can just duplicate it to meet the requirement of the network. The second thing you definitely need to do is change the number of units in your last layer. Okay, so here's one approach of doing this. You can take an existing CNN architecture, and then you can load the weights. So for example, AlexNet. And then you can freeze the convolutional and pruning layers, and then fine-tune the fully connected layers. Here, you can either randomly generate the parameters for the fully connected layers or use the values that are from the pre-trained model and then fine-tune the model. Option 2 is to take an existing architecture or implement your own, then pre-train on a data set, for example, a celebrity identification or a face identification or even expression recognition data set. Once you've done that, fine-tune on the problem that you're working on. The choice of the data set that you use for pre-processing is important, because if you pre-process on a data that is totally different, then the filters that will be learned in the convolutional layer will be useful in helping to discriminate between those classes and not necessarily useful in discriminating between facial expressions. The third option is to take a pre-trained model, either pre-trained on expression recognition or on a different data set, and then load that into memory, and then run the input image and extract features from a particular layer, say, for example, a max pruning layer, one of the later max pruning layers, and take those features and run it into another machine learning classifier. For example, AlexNet was often used. One study, for example, extracted 9,000 features from the last max pooling layer and fed that into an SVM. Authors commonly input their values into an SVM, although some have tried different machine learning algorithms, such as random forest. The advantage of this approach is that it's extremely fast. You don't have to train your CNN, you're just running it through the network and extracting features, and more time is spent on optimizing the additional machine learning classifier that you're using, which would probably be less than training a CNN. In terms of the literature, 30 studies reported that they use transfer learning, despite all the benefits that we know. AlexNet and VGG variants, such as VGG face, VGG16, were reported the most frequently. 6 studies compared using transfer learning and not using transfer learning, and in practically every case, using transfer learning led to an improvement in results. So on that note, I would definitely not recommend trying to publish another study that shows the difference between these two, because it's very well established. So there's no need to do this anymore. In terms of recommendations, I would definitely recommend using transfer learning as opposed to randomly initializing your weights. A good starting point is to use AlexNet or VGG face. If you're interested in the second approach of pre-training and fine-tuning, then I would pre-train on a face identification dataset. In terms of research, it would be very, or at least for me, I would be very curious to find out if you could take an architecture and optimize to which layer in the convolutional, between the convolutional max pooling that you freeze, and then to have an optimization algorithm to optimize the remainder of the network, as in to optimize the number of fully connected layers and the number of units given this frozen architecture, and to vary the setting in multiple experiments. Using existing weights means that you have long training time, so this can be avoided using transfer learning. And if you're interested in the third approach, then if you're extracting features, I would definitely recommend starting for SVM. Okay, so we've got all that done. Now we need to decide on network architecture. Constructing an optimal CN architecture is challenging. There's no real problem domain set of rules that tell you this is the architecture that you have to use in this problem. A CNN with few layers means there's few parameters, but generally means on average it's going to have slightly weaker performance than a deeper CNN, which is going to have more parameters, however also computationally more expensive. 26 studies did not implement their own CNN. This doesn't mean that they obtained the pre-trained weights. It just means that they were inspired by the architecture and used the structure of the architecture. So which architecture to use? Well, AlexNet was reported in 11 studies. There were VGG variants, 16 in face, and then other authors reported variants of Inception and ResNet. Once again, observations revealed that few authors provided rationale for their decisions. AlexNet was used, or at least it was reported to be used because it trains rapidly and achieves good accuracy. And 2 studies mentioned, for example, that they use VGG face because it's freely available and achieves good results. However, if you're interested in implementing your own, here are some statistics. So here I present the average, standard deviation, minimum, and maximum of the studies that implemented their own CNN, for which only one CNN was reported in the paper. So you can just pay attention to the average row. So here I show the average number of fully connected layers, convolutional layers, number of filters in the first convolution layer, the kernel size in the first convolution layer. So I'm only showing one value because the width and the height is typically the same, and the number of max pooling layers. So if I round these values up, I can say that on average, authors implemented 3 convolutional layers, for which the first had 42 filters of size 5 by 5, 3 max pooling layers, and finally 2 fully connected layers at the end. Okay, so the next choice is activation function. ReLU was used the most often. Very few authors attempted to provide a rationale for their choice, nor did they attempt to optimize the activation function. For example, 3 studies mentioned that they used ReLU to overcome the vanishing gradient problem, and others mentioned that it learns fast. In terms of the output layer, the softmax function was reported in nearly every single study. In terms of regularization, dropout was either used in convolution or fully connected layers in 29 studies, typically used more frequently in the fully connected layers. There were some other approaches, such as batch normalization or local response normalization. There was an interesting study here, and I would recommend reading it if you're interested in this field of research. They showed that applying max pooling dropout after every convolutional layer, dropout after every fully connected layer, and batch normalization after every layer achieves the best results. But I would recommend reading this paper because they only report the results in one data set. So I would definitely be curious as to repeat these experiments across multiple data sets, in a fair setting, of course. So in terms of recommendation, I would recommend starting with AlexNet. If you're interested in implementing your own, I would have 3 convolutional layers with 3 max pooling layers and 2 dense layers. For researchers, I would recommend comparing AlexNet VGG16, VGG face on multiple facial expression datasets, once again on both posed and non-posed datasets in a fair setting. I also recommend providing a lot of rationale, because authors did not provide a lot of rationale, which makes it hard to gain insight from the literature. And one interesting thing is there was a study that used depth-wise separable convolution. And the advantage here is that the number of parameters is significantly less than if you use traditional CNNs. So it would be very interesting to have a study that uses this type of convolution layers across multiple expression datasets. In terms of the activation function, I would recommend using ReLU, but I would recommend remaining up to date on different activation functions. Some authors try and come up with new activation functions which learn faster. Okay, so the last step would be on how you report your results. On average, the accuracy was reported in 83 studies. There were other authors that attempted different metrics, such as F-score, precision, and recall, but it was very unclear, and they provided very little rationale for these decisions. So the expression recognitions data don't really suffer from class imbalance, so there's really no need to try and cater for class imbalance using precision and recall. Accuracy is actually sufficient. So there's very little rationale for these decisions, and also it becomes very complicated to compare your results on studies that use strange metrics. In terms of validation, I would recommend using holdout. It was used in 42 studies. So here I mean either a chain test split or a chain validation test split. Careful cross-validation was reported quite often. The problem here is authors use different values of K. So some use 10, some use 8, some use 4. Some tried completely different things, such as leave one subject out, leave one sample out, leave one data set out. So here the key problem is it's very difficult to compare and to determine what is the state of the art when authors are kind of just doing whatever they feel like. Confusion matrix was used in 42 studies, and I like this because it can provide very useful insights as to what's going wrong and as to which expressions require more attention. Here, for example, you could say, okay, well, maybe I should collect more data on some of these classes that are doing very badly. Out of all the papers, happiness was classified correctly the most frequently, and the most incorrectly classified emotion was fear. This was typically classified as one of the negative classes, such as disgust or anger. So I would be curious as to find out the reason behind this. Is it because of a class distribution problem, or is there very little visual saliency between these different expressions? From the literature, I noticed this trend from papers published in 2016. They would do cross-database or cross-dataset experiments. Here you train on multiple datasets, and then you would test on a completely different dataset. Here the rationale was that reporting results on a single dataset is not actually sufficiently representative of how well your machine learning algorithm is. And in this experimental setting, most authors just reported on two of these experiments. So very few results. In terms of literature, a lot of studies did not mention what validation method they used, so comparison is practically impossible. On average, authors compared their results to 2 other literature papers. So once again, why so few studies? There were 2 studies that compared their results to Kaggle leaderboards. So I would be very curious to find out if in the future benchmarking against such online platforms could become a new thing. Because right now, if you want to compare against the state of the art, typically you would submit a paper and then you would claim state of the art and you would compare. But what if you're just, you're staying up one night and you've come up with an amazing architecture, you're not a researcher, you don't want to publish, but you've actually achieved a new state of the art. So is it possible that in the future this kind of thing will be a thing? So I don't know. 44 studies compared against their own CNN implementation as opposed to literature. So once again, why not compare to literature? I would definitely recommend using the accuracy metric. I would have a confusion matrix and normalize the values so it's easy to read the results. I would report on tenfold cross-validation across multiple runs. The rationale is that if you just report on one result, it is possible that you get a really good result by chance. And then if you claim state of the art, then it's really just not fair. And I would encourage authors to compare against other papers and other CNN studies as opposed to comparing to traditional methods, which a lot of authors have been doing. In terms of fairness, there were very few attempts at establishing benchmarks. So I found that authors did whatever, and no author stood up and said, we really need a standard. So here I propose a standard to run 4 experiments. The first one is a subject-independent test, where you split your data in such a way that subjects in the training set do not appear in the test set. The other is a subject-dependent test, where the same subject can appear in both the training and the testing, but not the same image. A more challenging task would be a dataset independent test where you have multiple datasets for which the same ones are not used in training and testing. And the alternative is to have a dataset dependent test where you can use the same datasets but not the same images. And this represents all possible combinations of what authors have been doing, except that this is definitely more fair if you have it in these 4 ways. And this definitely prevents authors from attempting to do their own splits, claiming state of the art, and then comparing in outrageous ways. And I definitely think that it is crucial to establish standards given the vast amount of studies that have been published in 2017. So to conclude, a lot of work has been done and there's still a lot of work to do. This is a very active field. There's a lot of publications in 2017. There's definitely potential for new state-of-the-art results across a large number of datasets on new datasets. There are other aspects such as ensemble methods and network and hyperparameter optimization, which I have not included in this presentation, so feel free to chat afterwards. There's definitely a lack of detail from the authors, so I think that authors should take responsibility and definitely report on everything and avoid being vague. There's definitely a need for a standard. And as a final remark, I'd like to just add that so you would read a paper and it would go something like this. Here are traditional methods. AlexNet achieved very successful in 2012, therefore we use deep learning. So I don't recommend using this anymore. So a lot of papers did this. So I think it is okay to say from all the publications in 2017 that deep learning works really great. And I encourage authors to come up with an alternative rationale for doing research. So I hope that the information I've showed in the various steps can help you implement a CNN for facial expression recognition. Thank you. Yeah. Yeah.
Just thought that there were someone classified in 6 different emotions, right?
Yeah.
Have you tried a clustering algorithm to see how many you can pick up in an unsupervised?
No. Definitely interesting area of research. Yeah. No one's tried that? Yeah. Your idea, you should publish it. Yeah. No. Nope. That your idea? Publish it. Sounds great. Yeah. The problem is that these datasets have very few. There was a study that showed that on very small datasets, transfer learning is not a good idea. On the datasets that have a little bit more images, transfer learning is definitely better. Beyond that, I'm not too sure. It would definitely be worth investigating further. Yeah.
So, two quick questions. The first is, I think calling for a rigorous experimentation like this is great, but I think there is a danger of basically starting to overfit between publications on your text data when you go to this machine. So maybe you can comment on that. And then the second question is, I think, again, you call for a lot of good experimentation. Do you think that this is really something that the computer vision reviewing community should actually address? Basically saying, because these papers are all published, right, I assume.
Yes.
So it's really, to a large part, the reviewer's fault that they are not.
Yeah, definitely. Okay, so for the second question, so I think I now call myself the literature police in terms of facial expression recognition in CNN. So if I were reviewing a paper and I saw this lack of detail, I would definitely ask the author to resubmit. I would blame the reviewers. One thing that I did not investigate is the impact factor with respect to how vague the results were. So that's like going really hardcore. And the first question was overfitting on standards. Well, you see, authors would be doing one of those four things anyway. So it just seems right to have those, to expect authors to do those four things so to establish fair comparisons. Because one author would be doing one thing on one data set, another author would be doing a different thing on the same data set. Now, how do you compare who claims state of the art? It's very difficult. Okay. Yeah.
You mentioned techniques like basic sort of calculations like flipping. In any of those papers, use generative models like maybe GANs to make their own images?
No. Yeah, so that's something that I'm personally very interested in. No study, at least as of like last week, did that. So I would definitely look into it. I think it's a very good idea.
So one of the techniques you mentioned was copy paste. Is that like is that an optimization for is that a pre-processing optimization?
So authors would crop with the rationale of trying to remove noise. So for example, your ears or your hair, which don't provide useful features in discriminating between classes. So they would just apply cropping like here. This is the wrong slide. They would just crop the four corners and then the center. And that's what they would do. They wouldn't try and optimize how to crop. It's just, let's just do it this way.
Yeah, an interesting processing technique that I don't know maybe you may have heard about it, but this is more in video, where you given a video clip, because most cameras have like foveated lens, so you just take the particles like the fovea with the video and you actually just chuck away all the noise. I wonder if something like that is being done for images as well. Because if you look at an image, you know the part that is interesting and all that stuff you just throw away.
No. Beyond cropping, I haven't seen any more sophisticated approach. Okay, at the back. Yeah. Yeah. Okay. No. Yeah.
The laboratory studies that you place satisfied that you express much confidence, those are normally constructed with facial action coding system. So they're really well constructed, well verified. And the other databases are wide. Who's determining what version of those
these datasets will be pre-labeled. So I do agree, a lot of these datasets have been made for action units. But in addition to providing the action units and they would provide the emotion labels. So the authors of the data set would have labeled the data accordingly. I'm not sure if that was your question.
That's right. Are you happy with that? There's sufficient verification that the emotions are what a set of people would agree on.
Okay, now I understand. Okay, so there was a study that used multiple taggers, and they attempted to determine the agreement between the taggers. As far as I recall, the percentage was less than 70. So roughly 70% agreement between multiple taggers. So there definitely needs to be an effort in terms of the number of taggers, and maybe when the authors release the data set to provide this information on disagreement between taggers and things like that. Yeah. Sorry?
What happens if we train the model on Archi image is used
Okay, so RGB versus grayscale. So essentially you just have more trainable parameters because you would have 3 input channels. So your first convolutional layer will have more parameters, your whole network will have more parameters. It's just more computational effort and you're not gaining anything extra. So it's just best to use the grayscale because you're not actually getting more information by using a color picture. Unless if you have additional insights, I'm not sure.
let's say if maybe if you used if you just wanted to use the same picture, just use the Archi image, or it doesn't matter how well
It wouldn't matter. I would just use grayscale for less parameters. That's the main argument.
I think it means like if you're training your system to use RGB and you use that same classifier on a grayscale, it will work.
I'm not sure. I think that applies to general machine learning, so not just facial expression recognition. So I'm not sure. I'm not sure. Can think about it.